two universal gates, NAND and NOR. We call them universal gate because we can implement any digital system by using NAND or NOR. Now I have to prove this statement. NAND and NOR are called as universal gates, and for this we will first revise basic gates. We have three basic gates, AND, OR and NOT. AND, OR and NOT are sufficient to implement any digital system. We can implement any digital system by using AND, OR and NOT. And if we can convert NAND or NOR to these three, if we can convert NAND or NOR to AND, OR and NOT, we can say that any circuit can be implemented by NAND or NOR alone. This is very simple. We can implement any digital system by using basic gates, AND, OR and NOT. And if I can convert NAND to NOT, NAND to AND and NAND to OR, if I can convert NAND to these three, I can say that NAND is universal gate. Because by using these three we can implement any digital system, and as we can have NOT, AND and OR, by using NAND only we can implement any digital system by using NAND only. And the same thing is applicable for NOR. In this lecture we will deal with NAND gate. In the next lecture we will deal with NOR. First I will implement NOT gate by using the NAND gate. Let's take two input NAND gate. The output Y is equal to A and B and its whole complement. If we have two similar inputs, then output Y is equal to A and A. This is the first input, this is the second input and its whole complement. A and A is equal to A. So finally we have A complement. So if we provide same inputs to the NAND gate, it will work as NOT gate. It will work as NOT gate if inputs are same. Very simple. So first we will make two input NAND gate. These are the two inputs and this is the output Y, and if the two inputs are A, let's say, then the output Y is A complement. So this is working as NOT gate. If the input is A, the output is A complement. Very simple. Now we will implement AND gate by using the NAND gate. And if you remember the NAND gate presentation, I told you we obtain NAND gate by complementing the output of AND gate. If we have AND gate and if we complement the output of AND gate, then this will work as NAND gate, A and B and its whole complement. This is something we have already discussed, and now we want the AND gate back. We want our AND gate back. So only thing we have to do is to complement the output of NAND gate. If you complement the output of NAND gate, you are going to get AND gate, because complement of A complement is equal to A. Very simple. So let's do this. First we will make NAND gate. I will make two input NAND gate, A, B, and the output Y, let's say it is Y prime, and it is equal to A and B and its whole complement. We want AND gate, so I will complement the output of NAND gate. Y is equal to A and B and its whole complement, and again we have complement. So finally we are going to get A and B, and A and B is what? AND operation. So this is how we can have AND gate by using the NAND gate, but we can only use NAND gate. So this NOT gate must be replaced by this circuit. So let's implement it quickly. This is the NAND gate, A, B, and I will use one more NAND gate with two similar inputs, and this one here will work as NOT gate, and the output Y is equal to A and B. And the combination of two NAND gates are working as AND gate. Now we will move to implementation of OR gate by using the NAND gate. Output of two input NAND gate is A and B and its whole complement. If you simplify this by using the De Morgan's law, you will get A complement or B complement. And OR operation is like this. So what we need to do, we only have to change this A complement to A and this B complement to B. So we can simply complement the inputs before giving it to the NAND gate. So we will complement the inputs. We will complement the two inputs first, A, B. So we have A complement, B complement, and then we will feed them to the NAND gate. So the output Y is equal to A complement and B complement and its whole complement. By using the De Morgan's law, Y is equal to A or B, which is OR operation. So this is how we can implement OR gate by using the NAND gate. And again we will do the same thing. I will replace this NOT gates by the NAND gate having the two similar inputs. So we have to use 3 NAND gates to implement OR gate. We have to use 3 NAND gates to implement the OR gate, and to implement NOT gate, 1 NAND gate is required, and to implement AND gate, 2 NAND gates are required. The next thing is implementation of NOR gate, but before this I would like to tell you that we have already proved that NAND is universal gate, because we have implemented the NOT gate, we have implemented the AND gate, and we have implemented the OR gate. We have already implemented the 3 basic gates, AND, OR and NOT, and we have done this by only using the NAND gate. So NAND is universal. We can implement any digital system by using the NAND gate. Now we will implement the NOR gate, and NOR gate is obtained by complementing the output of OR gate. If this is the OR gate, then we have to complement the output of OR gate to get the NOR gate. So in this circuit we have to complement this output Y. So let's do this quickly. This is very simple. First I will use 2 NAND gates acting as inverters. A, B are the 2 inputs. Then we will use another NAND gate whose output is equal to A or B, and then I will use another NAND gate working as inverter, and the output Y is equal to A or B and its whole complement, and this is NOR operation. Right. So to implement NOR gate, we require 4 NAND gates. To implement NOR gate, we require 4 NAND gates. Now we will implement XOR gate by using the NAND gate. I think we are pushing the time, so we will implement XOR and XNOR gates in the next lecture. Try to solve homework problems given to you and post your answers in the comment section.